In this recording, we read this datasheet together. The components is Texas Instruments LM5180. It's a 65 volts input, primary side regulated flyback DC-DC converter, and with 100 volts, 1.5 amp integrated power MOSFET. So it's the switching device. Switching MOSFET is integrated inside. I'm using these components in a recent design to boost some voltage. Also use these components before to step down for an isolated power supply design. I found it's very interesting. No, I'm not expert on this field, but I like to read the datasheet. I want to share something with you, my understanding. The features first is a very wide input voltage range, all the way from 4.5 volts to 6.5 volts. And when it's after it start operation, it can go down to 3.5 volts after it's starting up. So it's basically the output can be can boost the input voltage, also can step down the input voltage. Okay, because it's primary side switching. Primary side is regulated, so you only have one component across the isolation barrier, and it's 1.5% regulation, output regulation accuracy. You also have optional output temperature compensation, 6 milliseconds internal soft start, or you can use a capacitor to program the soft start time. Of course, the input lock-in voltage and thermal shutdown protection, all those. And the integrated MOSFET is 100 volts voltage rating, and the internal resistance is 0.4 ohms, 400 milliohms. And it's because the primary side regulated, so you don't need the optical coupler or auxiliary transformer winding for the feedback. So that's what I really like about these components. Of course, they have internal loop compensation, etc. And the very high efficiency at certain voltage, very low input quiescent current. It's capable single or multiple output, so you can have one input, two outputs, or one input, one output, or EMI. Okay, that's a typical application here. It's very typical flyback design. You have voltage input here, input capacitor, and you have soft start here. Internal soft start was used here, and you have an arc set to set the compared voltage, and you have a feedback resistor here for the feedback loop for the output control. Transformer in this case is 3:1 ratio, so it can step down to 5 volts. And here's a flyback diode, MOS diode, and also output capacitor. So it's a basic. It is just Zener diode plus a switching diode just for the protection of the transformer. Okay. As we said, it's a primary side regulation. It's very important here. It's not much new information here. And this is the typical efficiency curves and for output voltage 5 volts. And the output efficiency here depends on the output current for different voltage, input voltage, okay? And the highest voltage is when you have a lowest voltage difference between the input and the output. For example, if it's 12 volts input here, it's black curves, and you got for 5 volts output, for 0.2 milliamps, 0.2 amps current, you have efficiency about 85%. Okay. If your voltage keep increasing, the low output current efficiency is lower, but the higher current efficiency eventually reaches 85%. So basically, the is have higher efficiency and higher output current. When you work on really low current down to here, you're gonna really be careful that the efficiency could be low. Okay. Uh, Description, not much new information here. Let's move on. So that's a component. It's a very small component. It's a 4 by 4. I think it's a 4 millimeter by 4 millimeters. 8 pins. You have a switching pin. There's a switching node, feedback node, input node, enable pin or a voltage lockout, ground pin. This is set the reference, temperature constant, and soft start. Okay. Here is the absolute maximum ratings. This is also important, and the absolute maximum input voltage is up to 70 volts. Here, enable pin also up to 70 volts. Output voltage from the switching node up to the ground up to 100 volts. Okay, recommended operations. As we said, is okay, operates from all the way from 4.5 volts up to 65 volts input. And the switching node voltage can be 95 volts. Okay, there's some typical values, electric values here, supply current, very low quiescent current, and 3 microamps. When the device is shut down mode, the current is only take 3 milliamps current. So here's the enable and the input under voltage over voltage lockout, so it's not very critical. And the feedback we use, if you use a 12.1 kilo ohm set resistors, you're gonna have a set current of 100 microamps. The set voltage is 1.21 volts. We'll be using this a lot in the later calculations. Switching frequency all the way from 12 kilohertz up to 350 kilohertz. The minimum switch on time is 140 nanoseconds, so you better use a very fast flyback diode. Diode thermal composition voltage set state is 1.2 volts. And the power MOSFET all resistance 0.4 typical 400 milliohms. So soft start internal programming soft start 6 milliseconds. If you want to change this, you can use a capacitor to change. Another current limit, the maximum current, the inductor current is up to 1.5 amps, typical values. And the thermal shutdown and 175 degrees C. You have a hysteresis about 6 degrees. Okay, here is the curves for more efficiency with 24 volts input and I think it's for 5 volts output efficiency. Okay, and the current, it's a switching waveform for output 1 amps. That's the all switching. This is for the case with 448 volts input, 1 amps output switching forms. Okay. Startup characteristics. Okay. Not much new here. Junction temperature, active quiescent current. We can skip this for now. Okay, this is kind of important. MOSFETs are all resistant. The inside MOSFET are resistance versus temperature. So here, the temperature when the temperature goes up, the all resistance go from typical 0.4 ohms all the way to 0.6 ohms. So in the layout, you should try to actively manage the heat. Make sure not the junction temperature not too high. Okay. Here's the function diagram blocks. So we got input, capacitor. Here you have a comparators for the enable pins under voltage detection or voltage detection. And here we have the transformer here, the primary siding, primary windings and secondary windings, flyback diode, output voltage, output capacitor, Zener diode protections for the transformer. So switching node is here, the switching MOSFET is here. Okay, the MOSFET is all off here, and it's a primary sensing. So the sensing the primary voltage induced voltage and the primary side goes with feedback resistor, and it goes to here, go to the feedback, sampled feedback, and compare with the reference voltage, and to realize the regulation. Okay, 100 volts power MOSFET here, and the current sampling for the current limiting. Sets the 1.5 amps current limiting here. Here's a soft start, and internally you have a current source to charge up a capacitor to compare with the internal, to compare a voltage here to do the soft start. And also you have some LDOs here for bias regulators to produce the bias voltage, and internal compensation loop for the stability issues, and the iset resistor, and the temperature compensation. Okay, so the integrated power MOSFET, we said is 100 volts, 1.5 amp in-channel MOSFET, and during the MOSFET on time, the transformer primary current increase from 0 with this slope. If you know the inductors L, di, dt, right? So the voltage divided by L is the slope with the current change. It's how fast the current change. That's basically what we're doing here. And here we have a description for typical applications, and all this stuff in red here is optional. Okay, if you know if you know the transformer voltage, the feedback transformer, the primary side will not over the rate 100 volts rate, you can skip this clamping or protection circuitry here. But it's usually it's a good idea because the inductance from the transformer. The flyback can work on three modes, and depends on the load, how much power, the percentage of total output power. It can work in 3 modes. Okay. In my applications, it's very low power. I mainly work on this frequency fallback mode. And remember, the maximum switching frequency is up to 350 kilohertz. Okay, these are the details calculations about these 3 modes. And we jump to something very important for the applications. What feedback resistor you should use? The feedback resistor values would be the output value plus the voltage drops over the diode, and times the ratio of the primary to the secondary, and use then the resistance was the R set resistor divided by the V reference. Okay, R set is usually 12.1 kilo ohms. Okay, just skip on. And the soft start, we can see the soft start is internally have a soft start about 6 milliseconds. 6 milliseconds. If you will set the new soft start time, the capacitor you are going to use, you can calculate based on this equation. Milliseconds times 5, that's the capacitor value in nanofarad. Okay, optionally, you can either use the internal bias voltage, internal generated bias voltage, or you can use external bias voltage. That means you need another auxiliary windings from the transformer to produce this bias voltage. Normally, we don't Or at least I don't do this. Okay, there's all kinds of protections here. To jump to the applications, this is a typical step-down applications. It's for 5 volts 1 amp output here. 5 volts 1 amp. It's very typical, like the example we showed before. Okay, you have a 3-to-1 ratio transformer. Primary is winding 3 times more than the secondary winding. Okay, it's all typical values here. That's all the components in above circuitry. Gonna be careful to check the transformers. Make sure you choose the proper transformers. And for the circuitries based on the output voltage, you need to choose different transformer ratios. Okay, if the output voltage is 4 volts to 8 volts, it's 2-to-1. If it's for my case, I just isolations. I want to use 1-to-1 transformer for isolations. You can also step up to 55 volts and use a transformer. Secondary windings more than the primary windings. The vendors or Coilcraft, it's a high quality transformer from them. Okay. Here is actually design. You have tools to help you decide these parameters, but it's very easy to calculate based on the equations shown here. This is for the example above. How do you choose the transformer for the 5 volts output? Okay, and we have these equations. That's approximately 60% duty cycles. That means from one cycle is 60%. The MOSFET is on. The primary is charging up, and 40% it's off. So it's 0.6 and 1 minus 0.6. That's the minimum input voltage 10 volts. Output voltage 5 volts plus 3.3 volts from the flyback diode. Roughly you get the number 3. So that's can give you the primary to the secondary windings ratio. It's about 3-to-1. And how to choose the inductance of the capacitors, inductance of transformers, you base on these equations. So you get 5 volts plus 0.3 volts times 3, the primary secondary ratios, the minimum off times for 115 nanoseconds, the switching peak current, in this case 0.3 amps here for fallback mode. So you can roughly get 24 microhenry. Okay, if the transformer is bigger, have a primary inductance bigger than 24 microhenry, you should be fine. Okay, these are the current. How to choose the flyback diode? The flyback diode reverse voltage is decided by these equations. It's maximum input voltage divided by the primary to secondary ratio plus output voltage. In this case, it's 65 volts divided by 3 plus 5 volts output is roughly 27 volts. Okay, you also need to calculate the Zener diode for the clamping and the output capacitor. Okay, it's kind of critical to choose the proper output capacitors. In general, if the output voltage is very low compared to the input voltage, you want a larger output capacitor. If the output voltage is relatively higher or closer to the input voltage, you need smaller capacitors. Capacitors normally use ceramics capacitors. Okay. And the feedback resistor, we just use these equations. Output 5 volts plus the forward dropping over the flyback diode times the primary to secondary ratio divided by 0.1 milliamps. So in this case, 158 kilo ohm. So here, this 0.1 milliamps came from the reference voltage 1.21 volts and the 121 kilo ohm resistors. And the thermal composition resistors, because the forward voltage changing based on different temperatures, so you can use this equations based on the feedback resistor values, and primary secondary ratios, and you can calculate a composition resistor 130 kilo ohms. And here is all the calculations for under voltage, over voltage lockdown. Okay, this is application output current versus efficiency for the 5 volts output with different volts input. It's very typical. Again, the efficiency is relatively low and higher current, lower current. And when you go higher current, say 0.8 amp here, roughly the efficiency is about same at 85% with different input voltage. That's very, very good. Okay, this is all kinds of switching, voltage switching form, and the EMI radiation plots. Okay, here's a second example. It's a flyback converter with dual outputs, and so 15 volts and minus 7.7 volts. So it's another very typical application. If you want to produce a negative voltage, you can use this topology. And basically, you have one input coming, goes to switching, and the same stuff here, similar setting here. And the transformer, you have one primary windings and two secondary windings here. Okay, and the ratios, this is 1 to 1, this is 1 to 0.52. Okay, you see it's like a 50% less windings on this side. Okay, here. So that's why this is step down. So when you set the output, you base on this, you calculate the feedback resistance based on this 1-to-1 ratios, and naturally you will set the output for this second output here. Okay. Again, when you have a higher input voltage, so the relatively lower capacitor, output capacitor, lower input output voltage, and relatively higher capacitor, and say this everything here is inversed because it's a negative 7.7 volts output. Yeah, be very careful. Be very careful about the direction of flyback diode for a negative voltage. Okay, here's all the components we used. Again, so be careful with your proper choose transformers and proper input and output capacitors with the proper ratings. And the calculation for the transformer and everything, feedback resistors are very similar to the previous examples. Here's it's the efficiency curves, and similar is about maximum is about 85%. It's a switching waveform. So this is another samples with two outputs, but they are not one positive output or one negative output. It's two positive outputs, so you can stack them together to produce a higher voltage. Okay, so it's very similar. You need one primary windings, two secondary windings, produce 2 voltage. Yeah, so here's very similar calculation. Efficiency. Switching form, load transient, if you care about this stuff. If you have a very dynamic load, so the current draw from the power supply is changing from one current to another current in a very fast way, you should care about this load curve. Yeah, this is some power supply recommendations. In case your power source have a long cable, you should be careful with the ESR or the input capacitors, some layout guidelines. It's very typical layout examples here. I find it interesting. You remove the copper underneath the transformer, and you have large copper areas here, and for the heat dissipation, and the transformers are really large isolation gaps. Everything here is very tightly layout. Here's tightly layout. Yeah. It's a whole family even a flyback DC-DC converter based on applications. Yeah, I think that's all. That's a footprint. If we build your own library footprints, be careful. Have an exposed pad for the heat dissipation. Uh, yeah, that's all. Hopefully this can help you to use these parts.